Hi guys, today I'll be talking about Euler's method and how we can use it in some real equations. But before that, let me explain what the Euler's method is. So for reference, let's take a normal graph. So in this graph, there is x1, x2, and y1, y2. And in a normal gradient, in a normal tangent, it will be y2 minus y1 over x2 minus x1. So that will help you find a single point in the graph, an exact point. But it's very tedious for you to keep making points along the graph. Different tangents requires a lot of time. So that's where Euler's method comes in. Euler's method is not a precise measurement, but it's an approximation of the graph, of the curve. So it can be used. So this method is using yn plus 1 equals to yn plus h, which is the step size, which I'll get to in a bit, multiplied by the function of xn, yn. So actually, this function is just the gradient. Then we can scroll down to this other graph with the Euler's approximation. So you can see that the step size h is actually from x initial to x1 to x2 and so on. So this actually give you normal feasible differences in the numbers so they can create a proper approximation. So it can be simplified in this equation over here to sub in for this equation. So let's head over to a real life example. Okay, so we are here at the spreadsheet now. So let's try to do this question. So when dy dx equals to 2x over y and y0 equals to 1. Okay, let's solve this using Euler's approximation. So we set x initial as 0 because in the question it says 0 and y obviously equals to 1. So this function is actually 2 times c6, which is x, and over d6, which is y, because this will give us the gradients. Okay, so after this we can use the step size, which is 0.5. And the reason we are using such a small step size instead of 1 or 2 is because the smaller your step size is, the more incremental it gets and the more precise your value will be. So let's take this. So I will take the initial x value plus g, but I won't do the direct value because I want it to be incremental. So I use $3. Okay, so that's the first value. And for y, I'll do something similar. I'll take the y value plus g $3, but I'll multiply it by the gradient. Okay, then after this, I'll just drag this down. And okay, let's say you want to find when x equals to 5. Okay, what is this value? So you can drag down all the way, and actually we have hit directly on 5. Let me highlight this. So by the Euler's approximation, we can say that when x equals to 5, y equals to 7.08. Okay, let's take 7.08 first. Okay, and let's do some proper calculation. So we have this number by Euler's approximation, where y5 equals to 7.08122. So let's solve it in a normal way with a general formula. So we see that dy dx equals to 2x over y. So we do this, y dy equals to 2x dx, then integrate it. Then we have this. And from here, we can find the formula for this. So it will be y squared equals to 2x squared plus c. Then we can square root it into this formula right here. And after that, let's head over to find for c. So we take the formula that we got just now after integrating, and we sub in where y equals to 1 and x equals to 0. Then when we sub in, we realize that c equals to 1 over 2. So let's scroll down over here. So we see that when x equals to 5, which is what we're trying to find, x equals to 5, c equals to 1 over 2, and we sub in, actually it will equal to 7.1063. Let's bring it up here. So actually you can see that with a step size of 0.5, there's only a 0.2 difference in the amount, and the difference will only get smaller as the step size continues. And this is already quite a big step size. If I want to get an even more accurate number, I can get a smaller step size, but that requires more time and that requires more points. Thank you for listening.